Swayam Prabha. Digital India. Educated India.
Welcome to the 33rd lecture on the course NPTEL course on architectural acoustics. We are in the 7th week and this is the third lecture of the 7th week. The last lecture on the airborne sound transmission. So, the lecture title is the airborne sound transmission 3. So, the learning objective of this lecture are: we will describe this lecture what is the coincidence effect and what is the impact of the coincidence effect in the transmission loss of a partition wall. And we will try to formulate a methodology and to evaluate the value of a partition wall, that is called the STC, sound transmission class value of a partition wall. So, quickly go to the slide where we have already discussed this particular slide in the very first lecture of our sound transmission, airborne sound transmission. This transmission loss TL is depend upon two physical parameter. Of course, there are various others also, but these two are very important and very significant. One is surface mass of the partition wall and another one is the sound frequency. And as we understand that this per octave increase in the octave or the per octave the sound frequency of, if it is doubled from the lowered one, the transmission loss is increased by 6 dB. This is follow a kind of a steep straight line graph kind of a thing, where you can plot the frequency in the x axis and the sound transmission loss in the y axis, and you can see the transmission loss is something like this through this particular, follow this particular straight line, but in actually you will follow this green line where there is a sudden flat plateau and then again there is a increment. So, if you produce this line with the blue dotted line, this is the TL, the transmission loss as per the Mass law, and this green line indicate there is a slight change in the TL as per the frequency change, and there is a kind of a plateau is available here. And this is also true that the sound transmission loss is low in case of the low frequency. So, the sound energy passes through in a low frequency less, whereas the high frequency more sound energy passes through. So, there is a high TL value or sound energy isolation is very high. So, next is this case again, if I see this, try to find out why there is a depression, why this particular kind of the changes occur and what are the significant role of this particular change in a partition wall. We say we can see that there are three such the geometric parameter. One is this dip, which is called the coincidence dip, which is almost about 5 to 15 dB, and this is a width of the plateau, how much plateau will be long, it is shorter or the longer plateau. It depends upon the damping of this partition wall, how much damping of the sound is going to create, and this plateau height or this coincidence dip, this two plateau height in this particular coincidence dip is depend upon the stiffness of the partition wall, how much it is stiff, how much it is rigid. So, these three phenomena gives us a kind of a understanding that even if the frequency, if its frequency increases, the transmission loss is going to increase, but it is not same for all the range of the frequency. Somewhere it is kind of a a jerk, and then there is again it follow a particular straight line, and this particular phenomena is called coincidence effect. The coincidence effect is that suppose there is a partition wall, and by virtue of the partition wall the mass and the stiffness and the damping factor and all those the physical parameters, it has a shear wave capacity or the some vibration mode, and this vibration mode can be described with its natural frequency. And if the incident frequency of the sound, which is actually the incident sound wave, is matches with this shear wave or the phase of this particular vibration, then this frequency, the incident frequency and its own natural frequency matches together, then there is a resonating effect. Then the sound will going to pass through the maximum amount. So, that is why there is a sudden dip in this particular the TL value of the partition wall. So, what happened is that, so in any particular object has its own natural frequency, and if that matches with the incident sound wave, it passes a huge amount of sound because of the resonance, and this vibration of this particular partition wall will coincident, when it is coincident with the incident wave, it is called is a coincident effect, and due to that there is a gradual change or there is a sudden dip in this frequency and TL curve. So, a normal frequency TL curve will look like this. The initial in the short frequency range, there is a lots of dips and undulations. This can be described as there are some kind of a stiffness control and there are some kind of a localized resonance is can be happened. So, that is where there is some undulations. Stiffness control means suppose a wall having the same surface mass, but it is stiffened by some irregular interval by some structurally strengthened material, then this particular the partition wall can be act as a very stiffened, very rigid, and it can have a kind of a control in the particular frequency particular transmission loss. But if it is not stiffened, it is not in regular, only in the edges or maybe only one in between and only in the edges, then it is not that much of stiffen and there is a decrease in the stiffness and the TL values of so. But after certain amount of the frequency, after certain initial frequency band, if you leave with this kind of a disturbance, then it follow a straight line, and this is your mass law. As per the mass law, 6 dB increase as per the octave or the 6 dB increase as per the doubling of the mass or so. It will continue in some portion and then there is a dip, there is a coincidence effect. But this coincidence effect will initiate in a certain point and it will follow a dip or follow a plateau, and then again it will follow the curve, which is a 6 dB per octave or the 6 dB is the doubling of the mass curve. So, this line and this line is parallel, but there is a offset between these two lines. Now, this frequency where this particular coincidence effect is initiated is called the critical frequency, or that is the frequency of the natural frequency or the phase frequency of the particular wall, which matches with the incident frequency. So, if you have a different partition wall of different material, this critical frequency point may be somewhere here, maybe 500 or maybe in 4000. So, this may change depending upon the critical frequency point may change because of the nature and the material of the partition wall. So, we are landed up in a problem. The problem is, the number one is I need a single value of a transmission loss to design a particular noise barrier or a partition wall, single value. Why single number average value? Because that's helped me to decide, to get some kind of decision that which partition wall I will use for my purpose, for my noise reduction. But a single value average value of the transmission loss is always going to mislead me. Why it is mislead me? Because it is depend upon various frequency, and not only it is depend upon various frequency, there is a critical frequency also where there is a coincidence dip, and initially there is some kind of a disturbance because of the stiffness and the damping. So, if I calculate the average value for all the TL over the range of the frequency, it will definitely going to mislead me. But what is the way I can find out? So, still it is we are depending upon a single numbers transmission loss. Some methodology has to be established that can decrease this particular misleading phenomena, or it will just dilute some way, may not be, it will be accurate in nature, but still a single number transmission loss can give me a kind of understanding with some method that yes, this particular partition wall, if I use average in a term, in average term with maybe a 10% error, 10 to 15% error maximum, that give me this much amount of the sound reduction or the transmission loss. So, for that a standard system has been developed in United States, and that is called the sound transmission class STC via a STC contour. And this particular STC contour was developed with a proper straightforward and a very the step by step order methodology by the ASTM, the American Society for Testing and Material. So, we will discuss that how this particular the steps, the way this STC value of a partition wall can be formulated, can be found out, and any kind of the product, the partition wall product manufacturer and lot of the organization, those who are actually providing those kind of solutions for the partition wall solutions, or maybe the noise acoustical solutions for the room, they actually go for this STC number or the STC rating of the partition wall while designing any kind of the enclosure. So, there are 5 or 6 steps. The first one, we have to test a particular partition wall in a laboratory for various frequencies also, and the frequencies are 16 frequencies. It starts from 125 hertz to 4000 hertz. So, these 16 frequencies are all 1/3 octave band frequencies in between 125 to 4000 hertz. Then we have to plot a graph in between this frequency and the TL. Then we have to overlay STC contour, because this graph which is we will plot in the step number 3 will be a very haphazard kind of a graph. So, I have to actually slice off some of the points, and I have to go with a smoothing this graph with a kind of a contour, with a kind of a the different segment of a straight line, and I will find out the STC contour. And the fifth and final the step is that from that STC contour I can get the single value, that single value I am wanting for the STC value of the wall. So, all the 4 steps or these 5 steps has some typical methods or some kind of a rules, and we will describe that rules one after another. So, what is the first step is that we have to test the partition wall in a laboratory. So, we use that particular formula what we have used in the second lecture, the previous lecture. TL is equal to Ls minus Lr minus the 10 log alpha into S. So, this is the particular equation, and if I have a microphone at the particular receiving room and a loudspeaker in the source room. So, I can find out with a dB meter that what is the LS, that is the source room intensity of the sound, and what is the level of the sound in the receiving room. I can find out this, I know those values and As and alphas and everything, I can find out the TL values. And if I know the TL values, I now have a table where all the 16 frequencies are listed down, and I will find out all the corresponding actual TL value of all the 16 frequencies, and all the frequencies 16 is from 125 to 4000 hertz, actually covering the 1/3 octave band, and out of that these blue color ones are the octave band, the 125 to 50, in between that there are 2 1/3, and 250 to 5000 there are 2 octaves as 1/3 octave, like that. So, the 16 frequencies are those TL actual values has to be plotted. So, after you plot in the frequency versus the TL plot for those 16 octave frequency, you will get the graph of this nature, very haphazard kind of a graph, but even though this is a very haphazard, there is a tendency of moving up. I mean, this is the positive kind of a graph. So, as and when the frequencies increases, your TL values increases, but it may not follow a straight line. Probably at this particular point there is we follow a straight line, there is a kind of a disturbance over here, there is a deep and disturbance, and there is another disturbance because of maybe there is coincidence effect. So, there may be 1 or 2 coincidence effect in also. So, there are by virtue of the actual plot you will get those graph. But as I told in earlier, just taking the averaging of all those values will not going to help me, because there are some the phenomena, the coincidence phenomena and all. So, we have to go to the step number 4, where I will going to overlay a STC contour on that. I will be just going to cut off some of the points and try to fit some straight line in some the method with some method. What are the method? So, first in this the step number 4, the calculate the average TL value for the last 6 1/3 octave, that is 1250 to 4000. So, what I did is that you have to find out the average of this 1, 2, 3, 4, 5, 6, this last 6 TL value, and find out what is the average of that, and you plot the line. So, draw a straight line parallel to x axis of that particular, and find out this the AB line is actually the average of those. So, some points will be above AB, some points will be below AB. Now, let us go to the point number 4C. Plot the point C over 4000 hertz frequency and 5 dB below AB line. So, that means now you plot a point C over a 4000 frequency line, and this will be below B. How much below? Now, 5 dB below B. So, you see this from 1250 this blue line to this 400 this blue line, there are 1, 2, 3, 4, 5 gaps. So, the 5 gaps means per octave per frequency 1/3 octave there is a decrease of 1 dB. So, I got the point C, I will join the line BC also, the line segment BC is inclined and having 1 dB reduction per octave, 1/3 octave. Now, I have to go to the point D. Point D will be at this 125, the last line, and the drop will be now 15 dB. Now, this is again inclined line to C2D, and again from 400 to 125 there are 1, 2, 3, 4, 5 gaps. So, per 1/3 octave there is a 3 dB decrease per 1/3 octave. So, if you go to that, you see you plot the D over 125, 15 dB below, and join this point CD. The line segment CD is also inclined, having 3 dB reduction per 1/3 octave. So, your ABCD, the STC contour is completed. So, what I did is that all those haphazard point is now strictly in a disciplined manner I have formulated a contour, green contour line, which is STC contour, but this is not final. You have to see some criteria. To see get a single number of this STC, we have to find out some of the criteria. What we have to do in the step number 5a is that identify the frequency having the magnitude of the deficiency. What is the deficiency? The deficiency is that the difference between the STC contour and the TL value. So, I got this contour ABCD and this line is somewhere it is floating above and somewhere maybe it is dipping below your actual TL points. So, if it is floating above, so there is a deficiency. So, deficiency is defined as STC minus the actual TL. So, these are the deficiencies point, these are the deficiency point, but this is not the deficiency, this is where the TL is above your STC contour. So, you have to find out this deficiency in the 5b, step number 5b, sum of the deficiencies has to be calculated. What is the total amount of deficiency for all the 16? And we have to find out the total amount of deficiency is, and we have to check these two criteria. The first criteria is that the sum of the deficiencies is less than or equal to 32 dB, and second criteria is that the maximum deficiencies in any one band does not exceed 8 dB. These two criteria has to be fulfilled. So, if these two criteria has to be fulfilled, like, so the first sum of the deficiency, so this sum, the amount of this deficiency plus this, so this all sum of the deficiencies should be less than or equal to 32, and any one, I mean you have to check every one. So, the maximum deficiency probably this one or maybe this one should not be less than 6 dB, less than 8 dB. And at the final stage in the 5c, we have to, there are two situations. If all criteria, both the criteria is satisfied, if both the criteria are satisfied, we go to the next trial of the STC contour. We will increase the trial STC contour by 1 dB, and we will recalculate the or recheck the criteria or the step 5a and 5b and come again. And sometimes this criteria does not match with the criteria, the actual these deficiencies are may not match. So, then we will decrease the STC by 1 dB, and again we recalculate or do the step number 5a and 5b, and it is again a trial and error process, and finally, we have to stop at a particular point where both the criteria is fulfilled, matches, and we will find out the STC value for the 500. So, suppose this criteria is matches. So, I have removed those points, and this is the final STC contour ABCD, and then correspondingly 500 Hertz frequency, the value corresponding TL value will be my single value STC value of the wall. So, let us have a small example. In this example, what I did is that I have written down the actual TL value of a partition wall from 125 Hertz to 4000 Hertz, all the 16 1/3 octave band. So, by virtue of that, if you plot, you will get a plot like this. Again, you see in this plot there is some disturbance, there is a straight line portion, and there is again a disturbance, but this may be a coincidence dip, this is a coincidence dip. And I have written down all the values for all the 16 frequencies for, and in the x axis I have just mentioned the number of the frequency number, the band number. Now, if you remember the first step, what I have to did is that this last 6, this 40, 36, 33, 33, 45 and 47, just find out the average is 39. So, average of the last 6 frequencies 39. So, the next is that next point is that this 400 frequency, here the 400 frequency TL decreased by 5. So, it is 35 minus 5 and 1 dB decrease per octave. So, 38, 37, 36 like that, and this is 34. And then at 125 there is a 15 dB decrease from the earlier, and that is 19. Why 19? Because 34 minus 15 is 19. So, there is a 6 dB decrease per 1/3 octave band. So, 34, 31, 28, 25, 22 and 19. So, I can plot my STC contour overlay over my actual TL plot. And now, next step is that step of finding out the deficiencies. See here, this is above, this is also above, this is again above, there are again these two are above the STC. So, the above I do not want to take, above I do not having any interest, I have only interest in these dips. This is the deficiency from the STC line to the actual TL line. This is the point, this is the coordinate where I have to find out. So, I found out for all the, this is the frequency 1/3 octave band, actual TL value, my first proposed STC first trial values, and this 19 and this difference between 17 minus 19, suppose this is the first 17 and this is 19. So, deficiency is minus 2, minus 6, minus 7, minus 3, but here it is not deficiency, this is some increment. Suppose it is the 315. So, this 33 and 31, 33 and 31. So, those are positive. I am not at all interested with these positive values, only I am interested in those negative values. So, what I did is that I got the full range of the deficiencies, and all those red or the discolored cell, I got the summation of that. So, in the first trial my all the summation are minus 30. So, total deficiency is minus 32 dB, and the maximum deficiency among this is minus 7. So, what are the criteria? If you remember the criteria, the first criteria is that sum of the deficiencies is less than or equal to 32, is 34, minus 34. So, I have to redo the things, but the second criteria is fulfilled, it is not exceeded minus 8, it is just minus 7, but the first criteria is failed over here, it is minus 34. I should have, I mean there should be, it is should be restricted to minus 32 dB or so. So, what I have to do? The option is we have to go to the next option, next trial, second trial of the STC contour. So, this STC line, the green line I have developed, that has to be lowered down by 1 dB, and if I lower down by 1 dB, the deficiencies will be less and we have to recalculate. So, I have the second trial with me, it was the first trial, and the first trial I have the deficiencies are calculated minus 34, minus 7 and all. So, my second trial, what I did, I have just decreased the value, the STC contour by 1 dB. See, this is 39 over here, this is 38, last 5, 6, 38, then there is 34, that is 5, this 35, and this I go on decreasing by 1 dB, and from 400 onwards decreasing by 3. Very similarly, what I did over here, and let us see, in this case these are the deficiencies for the second case, and if you add up, this is minus 26 and the highest is minus 6, both satisfied the criteria. Now, both satisfied the criteria, and I can stop here, because I do not want to go to the further one less, because definitely that will be again satisfy the criteria. So, my second trial of the STC contour satisfy the criteria. So, on that line second trial, the corresponding TL value corresponding to 500 Hz is my the single digit STC value, and that is 34. So, the 500 line Hz line. striking to my this 34 this STC contour, and that's give me the STC value is 34 dB, and that is how I found out this particular transmission sound transmission class of a wall. The next one is if there is a hole in the wall. So, this hole will actually try to leak the noise. So, it is depend upon how much amount of noise will be leaked through the hole. Suppose it is a very wonderful partition wall made by double leaf and all those, and there is a hole that may spoil your total the amount of effort and all to reduce the noise from one source room to the receiving room. So, it is depend upon the percentage hole area SH by S1 into 100. What is this SH? The area of the hole. What is S1? The total area. The total area is S1, and this SH is the amount of hole, this ratio into 100. And what is TL1? TL1 is the transmission loss of the partition wall, this partition wall, and what is TLC is a combined transmission loss of hole when it is a hole. So, the TL1, the partition transmission loss of the partition wall is placed in the x axis, and the combined partition the transmission loss of the partition wall with hole is plotted in the y axis. It is again some set of graph has been standardized by virtue of some experiment. Suppose there is a graph. So, this is for the whole area is 0.1%. So, if it is 0.1%, so you can go with this graph. So, suppose 25% of the 20, if the TL of the partition wall is 25, if there is a 0.1% of the whole, it is little less than 25, maybe around 22, 20 or 24 or something like that. If it is 10, so it is almost 10, there is no significant change. So, as the whole area is increased and the percentage whole area is also increased, this particular graph will now lower down. See, if it is 1%, you have to take this graph, 2% this thing. So, 50% you see, if there is a 50% hole, so then there is a huge reduction. So, 30 is equivalent to almost 3. So, if there is a 5% of the hole is there, a 30 actual gives you almost about 12 or so. So, let us have a numerical problem. We have a door of 2 meter by 1 meter, and in this door this door is having 30 dB TL, and there is a size or the hole size, there is a hole in that particular door which is having 20 centimeter by 10 centimeter. So, the total area of the door is 2 meter square is 1, and total area of the hole is 200 centimeter square, and the transmission loss of the partition wall without the hole is 30 dB. There is a small typological error, this should be TL1 is 30 dB, and this percentage of the whole area is this. So, this is almost 1%. So, in that I have to see this 1% curve, the percentage of whole area is 1% curve, and as this is 30 dB, this transmission loss of the wall is 30 dB. So, this TL1 you have to actually, this is TL1 is 30 dB. So, 30 dB is this, and with corresponding to that percentage of the whole area is 1% whole area gives you the combined transmission loss as 20 dB, this is 20 dB. So, actually this particular hole of 20 centimeter by 10 centimeter over a door of 2 meter by 1 meter destroy almost 10 dB sound. I mean, there is a leakage of 10 dB sound. So, that is all for this particular portion. So, I have noted down some of the partition wall significant character. You have to increase the surface mass of the partition wall to establish reasonable maximum to get a good amount of TL. These are some of the partition wall design criteria the guidelines. Double leaf partition wall is better than the single leaf, because there is a air cushion in between. So, the doubling of the mass is also happening, and there is a internal air cushion. So, that also improve the quality of the partition wall or the TL value of the partition wall. So, this is very important if you go with a double leaf kind of a thing. The air gap between two leaves may filled with some kind of a acoustical blanket. So, it also enhance the total amount of the transmission loss. The proper stiffener, as you know, the stiffener attachment will actually reduce those kind of initial disturbance. So, the stiffener arrangement is required, and this fixing of the partition wall with the wall or the ceiling has to be proper, because of the minimizing the coincidence effect in the zone of the actual middle frequency, and noise leaks that has to be checked, because as you know, if there is any kind of a hole or any kind of a noise leak, there is a decrease in the potential amount of the TL value. So, let us go to the last page, where I have again two homework for you. One is, you please write down or try to understand the what is the significance of the STC, sound transmission class value, and the second one is that if the average TL value of the last 6 contour, the last 6 the frequency, the 1/3 frequency of a partition wall is 35 dB, then what could be its STC value if all the criteria is fulfilled. So, that is all for today. So, the airborne sound transmission is with this 3 consecutive lecture number 31, 32 and 33 is now came to an end. In the next lecture on in the 34th lecture and the 35th lecture, we will discuss about the structure bound sound in this week. So, thank you very much.